Hi guys, if you are involved in designing experiments, especially in the field, one such kind of experimental design is what we call the CRD, or Completely Randomized Design. So what is CRD? CRD means Completely Randomized Design. It is used in experimental designs where the conditions are uniform or homogeneous. Example, when you compare the growth of a certain species of plant grown in pots with the same soil fertility and volume of soil, the system is homogeneous, more or less. That is where we can use CRD. Now, let's make an example, an actual example, a study on the effect of NPK or nitrogen, phosphorus, and potassium on the yield of corn plant or maize. Now, these are the conditions that we should think about when we are using the CRD. The corn plant will be planted on the same kind of soil, and we will be doing that in the greenhouse. The same seed size, type, and maturity will be used in this experiment. The treatments will be different. In terms of amount of NPK that will be applied on different treatments. So an example, there will be 5 treatments like control, meaning no application of NPK. And we have treatments 1, 2, 3, and 4 with an increasing level of NPK per hectare. Each treatment will be replicated 3 times. The experimental design, of course, will be using the CRD. And to obtain a uniform method of sowing the seeds, the same size of plots will be used with the same soil type. Our analysis will be the ANOVA, or analysis of variance, used for testing the significant differences between the means of the different treatments. And if we have a significant result where null hypothesis is rejected, we can continue with the post-hoc test. And in this case, we can use the LSD, or least significant difference. Now, let's check our hypothesis. We have null hypothesis and alternative hypothesis. Null hypothesis means there will be no significant difference when you look at the means of the result of the treatments. While alternative hypothesis, at least one mean is different, or there will be significant difference on their means. The significant test analysis will be using the alpha value of 0.05 level of significance, and we'll be also using the statistical tables, F table and T table, that will be used in the analysis. Remember, if in the analysis of variance you obtain a calculated value which is greater than the tabulated or given value, the null hypothesis will be rejected. Now, let's check the data. In the table, you can see the different treatments. Control, meaning no treatment. Treatments 1, 2, 3, and 4. So we have 3 different replications. And we have, for control, we have a treatment total of 15, treatment 1, 20, treatment 2, 27, treatment 3, 31, and treatment 4, 41. If you add all these entries in the 3 replicates, or you add all the treatment totals, then you'll find 134. And to find the treatment means, the treatment total is divided by 3, which is the number of replicates. So in this case, you'll have the treatment means on the last column, and the grand total, or 134, divided by the number of entries, in this case 15, you'll obtain 8.93, and that is what we call the grand mean. Now look, we have the number of treatments 5, the number of replications is 3, the grand total is 134, the grand mean is 8.93. Now, this is a sample computation from the table that we have seen. So here, if you add 5 plus 7, 12, up to 15, you'll obtain 134, and that is what we call the grand total. And the grand mean, of course, will be grand total divided by the number of entries, which is 15, so you'll get 8.93. And we just add the entries for each treatment, so you obtain the treatment totals here, shown in the computation. Now, since we are going to use the ANOVA, or analysis of variance, we need these components in the calculations. One special consideration is what we call the statistical correction factor. I will be using CF. The formula is grand total, you square that, divided by the number of treatments multiplied by the number of replications. So in this case, GT squared divided by K multiplied by R. K represents the number of treatments, R represents the number of replications. In other words, the correction factor will be 134 squared divided by the product of 5 and 3, and will obtain 1197.07. That's the correction factor. Another entry in the analysis is what we call the total sum of squares. So all the 15 entries, we take the summation by squaring its number and then subtracting the correction factor. So in this case, when we sum up the squares of the values from 5 squared to 15 squared, as seen in the table previously, minus the correction factor, the total sum of squares will be 152.93. The treatment is the sum of the treatment total squared divided by the number of replicates minus the correction factor. So you will see here the treatment totals 15 squared up to 41 squared. The sum of these squares divided by the number of replicates minus the correction factor, it will yield 134.93. And the most important thing here is the error is S, or sum of the squares of the error. This is obtained by subtracting the treatment is S from total is S. So you'll get, in this case, you get 18. Now let's go to the ANOVA, or analysis of variance. The source of variation are the treatments and the error. And we have the degrees of freedom, where the number of treatments minus 1, that will be 5 minus 1 is 4, while the error is taken as the number of treatments multiplied by replicates minus 1. So that will be 5 multiplied by 3 minus 1 is 10. and the total is will be the number of treatments multiplied by the number of publications minus 1. So that will be 15 minus 1 is 14. So that's how we get the degrees of freedom. I have a separate video on the meaning of degrees of freedom. As we have calculated, these are the entries that we can use in your analysis of variance. So we have total is S, treatment is S, error is S. So you'll have here sum squares for the treatment, 134.93. So it's here. And the error is S is 18. If you take the total, you'll have 152.93. All right. The MS or mean squares are obtained by dividing the sum squares by the degrees of freedom. So 134.93 divided by 4 will give you 33.73. That will be your mean squares for treatments. For MS error, 18 divided by 10 will give you 1.8. How do we get the calculated value or F calculated statistic? That will be 33.73 divided by the error MS error 1.8, and you'll obtain 18.74. We have the tabulated value or F tab. This tabulated value is obtained in the table. We call it F table of significance, and we'll be using, by the way, an alpha level of 0.05. Now let's check where we obtained this 3.48. We call this the F table at 5% significance level. Now check the ANOVA. We have the treatments, degrees of freedom 4, and we have the error, degrees of freedom 10. So we have to look for the numerator 4 and denominator 10 in the table. So you'll have 4 and 10. So the intersection of the value of this degrees of freedom of the treatment and the degrees of freedom of the error is 3.48. That's why we have here the tabulated value of 3.48. We customarily compare the calculated value versus the tabulated value. In our computation, we obtained 18.74, which is very much larger than the tabulated value. If this F value calculated is greater than the tabulated value, we say that there is a significant difference between treatment means, but we cannot say which of which are significant from each other. So we have to continue in what we call post-hoc analysis. So the calculated F statistic or F value is greater than if tabulated at 0.05 level of significant test. Therefore, we reject the null hypothesis and we accept the alternative hypothesis in this example. When we analyze at 0.05 level of significance. So, since there is a significant difference and null hypothesis is rejected, we will continue to post-hoc test. Post-hoc test is conducted to determine the significant differences between treatment means. So in this post-hoc test, the first thing that we have to do is to check the standard errors, and in this case we'll be using the LSD, least significant difference. technique. So how do we start? First, we calculate the standard error of the mean. So we have the simplified calculation. So check the MS error in the ANOVA table. See, you have MS error is 1.8. Okay, so the number of replicates is 3, so 1.8 divided by 3 and take the square root, you'll obtain 0.7746. And we continue by calculating the standard error of the difference, which is the square root of 2 multiplied by mean square, or standard error of the mean. So that is 1.41 multiplied by this number, and you will have 1.092. To find the LSD value at 0.05 significance, we will look for the T table at a certain error for the degrees of freedom multiplied by this number here. So we obtain 2.23. So how do we get this 2.23? We obtain that from T distribution table, or we call it the critical values of T at 5%, and we check the degrees of freedom of error 10, and the value is 2.228 or 2.23. So that is where we obtain this 2.23. So that will be the value for your LSD, which is 2.44. By the way, we use this value, uniform value for LSD, because the treatments have the same number of samples or the same number of replication. So this is where we obtain this value here, 2.23. Mean comparisons are shown in this table. We compare the difference between two treatments. In this case, we have treatment 1 minus treatment O, or control. Likewise with other treatments, and we can see the difference on the second column. The calculated less significant difference, or LSD, at 0.05 level of significance is 2.44. If the calculated LSD is greater than the difference, we interpret it as not significant, meaning the two treatments do not differ significantly from each other. If the calculated LSD is less than the difference, it shows that the two treatments being compared, they are significantly different in terms of the treatment means. By the way, the use of this format is applicable to treatments with the same number of replicates, or the same number of sample replicates. We summarize the previous table in making the report. We call this summary table. We have the treatment on the first column and the means on the second column. The superscripts shown means when scripts are similar, they are not significantly different. So we can interpret that the treatment 1 and control have the same designated letter A, so they are not significantly different from each other. Likewise, treatment 1 and treatment 2 showed no significant difference, as well as treatment 2 and treatment 3. However, treatment 4 showed that it is significantly different from the rest. So it shows that treatment 4 has the best impact or result when we use the different levels of fertilization to corn or corn plant. Thank you very much, and watch for more video uploads on statistical calculations. Thank you.